Alright, today we're talking about heat engines and the second law of thermodynamics. This is a little bit longer and more mathematical than most of the presentations I've done, but it's really cool. We're learning some really cool things. Heat engines are a totally relevant application of thermodynamics. Your automobiles are heat engines. Alright, so we're going to learn how to make a simplified model to help understand them. And the second law of thermodynamics is really cool because it's kind of an abstract thing that you can do real things with. The second law is one of those things that a lot of people know about, but they don't understand. It's like E equals mc squared. Everybody says it, but when you understand it, as you will when we get to the modern physics section, you'll be unique and you can tell people, oh, do you know what that actually means? You're going to learn how to do that with the second law of thermodynamics in the next few lectures. Alright, so what is a heat engine? It's something that converts heat into mechanical work. For example, in your automobile, gasoline is burned to make a hot gas. That hot gas then expands and does work, drives the drivetrain. So the purpose of your internal combustion engine in your automobile is to first it turns the chemical energy in the gas into heat, and then it uses that heat to generate mechanical work. So here's kind of a simplified schematic of what goes on in a heat engine. We have some thermal reservoir, some source of heat, something hot. All right? Heat flows from that thermal reservoir into our heat engine. Some of that heat is just energy, right? Some of that heat comes out as work, mechanical work, and then the rest of it gets exhausted down to a cold reservoir. Okay? So, by conservation of energy, the work that comes out of our heat engine is just going to be the heat that comes in minus the heat that goes out, right? Pretty simple. We also like to define the efficiency of a heat engine. The efficiency is just the fraction of the heat that you put in that actually gets converted to work. So it's just going to be the work divided by the heat that we put in. The thing that we want divided by what we put in to get it. Now there's a few things you should note. First of all, as we're going to find out in a few minutes, it is impossible for a heat engine to have unity efficiency. The work you put in, the work you get out will always be less than the heat that you put in. Another thing to note is that we're doing some kind of different sign conventions than we did previously. So previously when we talked about work and heat, positive work meant work was done on our gas, on our piston, and negative work means work was done on the environment, that energy left our piston, all right, because of the work. And positive Q always meant heat flowing into the piston. But when we talk about heat engines, it just makes sense to let work be the heat, the work that comes out of our piston, right, out of our system. And so we're kind of reversing what we mean by positive work when we talk about heat engines, so be aware of that. Also, Q hot is the heat that flows in. When it's positive, it means heat is flowing in from our hot reservoir into our engine. That meets our convention of positive Q being heat flowing into the system, but Q cold is positive when heat's flowing out of our system into the cold reservoir. So we kind of flip our convention for Q cold. But it makes sense for a heat engine, right? Because this is the way heat flows, this is the way work comes out of a heat engine. So don't get caught up in that. Okay. So now I'm going to do an ultra simplified example of a heat engine. All right, real heat engines have PV diagrams that are much harder to do calculations with. So I came up with kind of what's the easiest thing to calculate just to give us an example and help us understand the basic idea of heat engines. So here's the heat engine I've devised. Here's a heat engine. I've got this piston and it's going to go up and down to do mechanical work. And the work we're going to have it do is to raise a mass. All right, imagine we're in a mine and we have an ore cart. We fill it full of ore, we want to lift that ore up to the surface, and then we want our piston to reset so we can do it again. It's a cyclic process. It needs to do it over and over again. And let's figure out how much work is done in one cycle. All right, so the first step, we start off at some pressure and some volume. So this is gas in here holding up a piston. All right, and we're going to drive our ore cart onto the piston. As we do that, we don't want the piston to sink, so what we're going to do is we're going to heat up the gas. We're going to have heat flow in so that as the ore cart drives on, the temperature increases, such that the pressure increases to keep this from falling, right? On our PV diagram, we say, look, the volume didn't change, but we increased the pressure to hold up more weight, all right? So on our PV diagram, we go from point A to point B in an isovolumetric process. The next thing we're going to do is we're going to insert even more heat in to lift the piston up to the height that we want. All right, so we're putting more heat in. Now, what's staying constant is the pressure, right? The pressure is just enough to hold up the piston and the cart and the mass on top of it. Okay? So, what does that look like on our PV diagram? The pressure doesn't change. The pressure is just big enough to hold all this stuff up, but the volume is increasing. So that's going to be an isobaric process. Next, we need to get our ore cart off, right? And so we drive it off. And as we do it, we're going to let heat come out to get the pressure to come down so that as it comes off, the piston doesn't shoot up. It's going to stay at the same volume. So as we move the ore cart off, we have to reduce the pressure of the gas to keep the volume constant. All right? So we do that, heat comes out of the system, and we do another isobaric process to get us back to the original, well, not to the original pressure, but back down here, all right? Now, the last thing we need to do is we need to cool this gas down to get back to our starting point so that we can do it again, so we can lift another ore cart. So we pull even more heat out, and as we do that, this system shrinks, all right? Okay, what about the pressure? The pressure is going to remain constant. It needs to be just big enough to hold up the piston, but the volume is going to change. So we do another isobaric process. So our cycle is like this, all right? Now let's think about this cycle, A, B, C, D. How much work is done by this cycle? Well, we lifted a cart of mass m against gravity, a height h. So we know that's how much work is done. But now let's think in terms of the gas. To figure out the work done by the gas, we look at the work from each of these processes and add them together. What is the work done as we go from A to B? A to B is an isovolumetric process, so the work done is 0. There's no work done. When we go from B to C, the work done is, well, it's an isobaric process. And as you'll recall, for an isobaric process, P comes out of the integral, and we just get something that looks like negative pressure times the change in volume, right? In this case, what's the pressure? It's going to be the pressure at B, and the volume changes as we go from B to C. But I'm going to get rid of this minus sign. Why? Because remember, with heat engines, positive work means work coming out of the system, not work going into the system. So I have to change the sign of my work. All right? Okay, but we're not done here. What is the pressure at point B? At point B, that's when I have the cart onto the piston. All right? So the pressure has to be big enough to hold up the mass of the cart plus the mass of the piston. I'll use capital M for the mass of the piston. So if that's the mass it has to hold up, the force it needs is the force that's pushing down with, right? So there's the force due to gravity, that mass pushing down on the gas. So that's the force, and to find the pressure, I just divide that by the area of my piston. So there's the pressure, and what's the change in volume? Well, I go from here to here, right? So I go up a height h when I go from B to C. So the change in volume is just going to be the area of my piston times how far I went up. So A times h. Or in other words, the a's cancel, and the work from B to C is just going to be m plus the mass of the piston, gh. All right? What about the work from C to D? From C to D, once again, that's when our cart's rolling off, the volume doesn't change, it's isovolumetric, and so the work is 0. But when I go from D back to A to reset, that's when my piston cools down and it comes down. Once again, it's an isobaric process, so the pressure is going to be the pressure at D, or equivalently the pressure at A, times the change in volume from D to A. All right? But the pressure at D, or the pressure at A, that's when there's just the piston, no cart. So that's just going to be the mass of the piston times G divided by A. And the change in volume, when I go from D to A, it's A times H, but now it's negative. The volume is decreasing. All right? So this is just going to be equal to negative capital MGH. All right, so the total work done by our piston is the sum of all of these. 0 plus 0 plus the mass of the ore cart plus the mass of the piston times GH plus the work done from D to A, which is negative the mass of the piston, GH. And those cancel out, and I'm just left with MGH. So using my understanding of ideal gases, we were able to calculate the work done, and it turns out it's exactly what we thought the mechanical work done should have been. So it worked out. All right. What is the work done? We calculated that. How do we find Q hot, Q cold, the efficiency, and whatnot? Okay, so to find Q hot, when does heat flow into the system? It flows in here and here, right? It flows in when we're heating it up to keep the piston from sinking down as the cart rolls on, and we put heat in as it expands to move the cart up. We take heat out when the car rolls out and when it comes back down, right? I'm not going to do the calculations. I chose this example because calculating work was easy. Calculating Q hot and Q cold is a little more entailed. It's not impossible though, all right? But you can calculate them just by saying, here's when heat flows in. I take all the places where heat flows in, that's Q hot. Take all the places where heat flows out, that's Q cold. And again, efficiency is just work divided by Q hot, all right? And remember that work is Q hot minus Q cold. So if you could calculate just Q hot, work was easy to find, then it's easy to get Q cold and whatnot, all right? What is power? When we talk about the power that an engine puts out, that's work per unit time, right? So I just take the work that comes out in one cycle divided by how long it takes to do one cycle, and that's how we would find the power output by an engine. Okay? All right, so there's an example. Now, we already learned the first law of thermodynamics, and it basically said energy is conserved. So if I have some ideal gas, the change in internal energy of that gas is just the work done on it plus the heat that flows into it. Now we're going to give you the second law. And the second law says it is impossible to convert heat completely to work. In other words, there are no perfect heat engines. All right? Now, some people will apply this to like electric cars. All right? But an electric car does not use a heat engine. It uses an electrical engine. So the second law doesn't really apply. All right? The second law applies to heat engines, and it says there can be no perfect heat engines. In fact, not only can the efficiency not be 1, there is actually a limit which is less than 1. All right? So the second law of thermodynamics says even the ideal perfect engine is going to have an efficiency which is less than 1. What is that efficiency of your ideal heat engine? Well, Carnot thought about this. This is what Carnot worked on, and he said to himself, he was thinking of steam engines in his day, and he came up with this idea. A reversible engine is one that works as well backwards as forwards. If you could make a reversible engine, no engine operating between two thermal reservoirs can have more efficiency than that reversible engine between the same two reservoirs. And all reversible engines will have the same efficiency. Okay, that's lots of words. Let's think about this now. Instead of thinking about heat engines, let's think about water wheels. I've heard it explained this way, like this analogy. Imagine I have a river up here and a lake down here. All right? I can take a water wheel, right, and I can have the water flowing down, turn the wheel, and have that do work. All right? Now, imagine I have an ideal water wheel. It does the very best. It's completely reversible. All right? So a reversible water wheel, if I have two of them, I could take one water wheel, right, connect them together, and water comes down here. It puts energy into this wheel, which turns this wheel, which is then going to bring the water back up to the same height. All right? Now, real water wheels aren't perfect. Energy is lost. But if I could make an ideal reversible water wheel that worked equally well backwards and forwards, I could take my water, it comes down, and then I use the energy I got from the water coming down to take some other water and put it back up again. And if my water wheel if I could actually make an ideal one that was reversible, I could bring up as much water as I brought down. All right? Now let's think of that in terms of thermodynamics. Imagine I have some hot reservoir and I have some cold reservoir. If I had an ideal reversible heat engine, right? Some heat flows in here, some work comes out, some heat is exhausted. If I had a reversible engine, I could take another engine, all right, and use that backwards. If I run my engine backwards, I'm going to pull up some heat Q cold, and, all right, then exhaust Q hot back to the hot reservoir. This is actually what a refrigerator is. We put work in, and it uses that work to pull heat from somewhere colder and exhaust heat somewhere hotter. All right? If I could make an ideal reversible engine that worked equally well backwards and forwards, then I could do this, right? And if you zoomed out so you couldn't see the engines, you'd see no net heat flowing from T hot to T cold. And you'd be okay with that. You'd be like, okay, so there's no way for heat to flow. I'm happy with that. But now imagine that I have my, we'll call it a Carnot, let's call it a reversible heat engine running backwards, all right? If I have an identical one here, the effect is nothing. There's no net heat flowing either way, right? But now imagine that you invented an engine that was a little bit better than that reversible engine. So now you put some Q hot in, you get a little bit of extra work, which means if you exhaust a little bit less heat, right? But if you put in additional work, that's going to pull more heat up and exhaust more heat up into the hot reservoir. So basically, if you had a reversible engine and then you found one that was more efficient than that reversible engine, the two of them together could spontaneously make heat flow from something hot to something cold. It would be like saying I have an ideal reversible water wheel and then I have one that's even more efficient from that. I have a little water go down and I bring even more water back up. So this device with no energy lift water, more water than went down. So spontaneously water is going from a lower place up to a higher place. That's the basic idea. So Carnot comes up, his brilliant idea is, if I can come up with even a theoretical engine that's reversible, but works equally well backwards and forwards, that engine will have the best possible, even in theory, efficiency. Because if I had one that was even better, even in theory, I could conceive of a situation where I put the two of them together and without any outside work coming in, I can spontaneously make heat flow from something at a lower temperature to something at a higher temperature. So that's Carnot's big idea. He says if I can come up with a reversible engine, that engine will have the theoretically best efficiency. So Carnot thought for a long time and thought, what would be an ideal reversible engine? And this is what he came up with. An isothermal expansion, followed by an adiabatic expansion, followed by an isothermal expansion, followed by an adiabatic compression. All right, so something like this. We start at point A, we do an isothermal expansion to B, adiabatic expansion to C, isothermal compression to D, and then an adiabatic compression to return us back to our starting point and finish the cycle. All right? These are things that can be done reversibly. If, for example, I have a free expansion is not reversible, right? How do I know a free expansion is not reversible? If you filmed a free expansion and then played the film backwards, you'd be like, that's not how it works, right? The gas doesn't spontaneously go to one side of the container so I can put the lid back on, right? But if I have a piston, all right, and it's in thermal contact, let's imagine I have a piston in boiling water, all right? This is 100 degrees C, my gas is at 100 degrees C. If I let the piston expand, so imagine it's got pressure that's trying to push it up, and I let it push up a little bit. As it expands, heat flows in, all right? So I'm doing this reversibly, so very, very slowly. I see this is at temperature T hot, this is at temperature T hot, and heat is flowing in. That's perfectly fine, right? Because we're doing an infinitesimal change. As this expands, heat flows in. If you played that backwards, you would see this piston going down, it's at temperature hot, and heat is flowing out. That's exactly possible, right? That's not weird. You'd say there's nothing more weird about heat flowing out at constant temperature than heat flowing in. So an isothermal expansion at constant temperature can, in theory at least, be done reversibly. An isothermal compression, same thing. Imagine I have some gas at T cold, and I'm going to compress the gas while it's in thermal equilibrium with ice water, right? As I compress the gas, heat flows out, all right? It's okay for heat to flow this way because these are at the same temperature. If I do it backwards and play the film backwards, it looks the same, all right? So it is at least in theory possible to do an isothermal compression reversibly. Adiabatic processes, right? No heat flows in or out, so if I just take my piston, it's not connected to the world, I squish it down or I let it pop up, it looks the same. running backwards and forwards. Both ways don't violate physics, all right? So here's my reversible process that Carnot comes up with. So here's a theoretical heat engine that is reversible. So if I calculate the efficiency of this heat engine, that is the best efficiency you could possibly get with a heat engine. So let's see if we can calculate the efficiency of a Carnot engine. All right? First of all, to do this, remember that efficiency is just work over Q hot, which work is Q hot minus Q cold. We can also write it as then 1 minus Q cold over Q hot, right? So, to find the efficiency, I need to find Q cold and Q hot. When does heat enter or leave the Carnot engine? Well, if you look at the adiabatic processes, Q is 0, so we don't have to worry about them. Isothermal expansion, as it's expanding, in order to keep the temperature constant, heat has to flow in. So here is when we get Q hot. Compression is the opposite. As we compress it, the gas is going to want to heat up. In order to stay at the same temperature, heat has to flow out. So here's where we get Q cold. So Q hot is from A to B, and Q cold is from C to D. All right? So, what is Q hot? Q hot is the heat that flows in when we go from A to B, right? And how do I find that? Well, remember the first law of thermodynamics. Change in internal energy is Q plus work. What is the change in internal energy for an isothermal process? Remember, the change in internal energy is always N CV delta T. So for an isothermal process, the temperature doesn't change. There's no change in internal energy. So the heat is just going to be equal to minus the work. All right? Minus the work. All right? Okay. But, so the heat from AB is going to be equal, Q hot is equal to heat from AB, which is equal to the work when we go from, minus the work when we go from A to B. All right? And that is going to be equal to, well, negative, work is negative integral from V initial to V final P dV, right? And as we found before, so this is just going to be equal to NR, the temperature, times the natural log of the volumes. All right, we're going from A to B. So what's the temperature at A? Well, we really only have two temperatures. We have multiple temperatures, but the hot, all along this constant temperature process, the temperature is going to be the hot temperature, and all from C to D, the temperature is going to be the cold temperature, right? So the temperature that this happens at, we'll just call it T hot, and then we take the natural log of the ratio of the volumes. As you recall, when we did this integral for a constant temperature process, that's what we got, all right? And so we're going to a final volume of VB, and we start at a volume VA, all right? So there you have it. That is the heat that flows in. Now, Now, the heat that flows out, how do we find that? Well, it's basically the same thing. It's going to be NR, only now it's done at a temperature cold, natural log of the volumes for Q cold. We're going from C to D, right? So it's going to be volume of D divided by the volume at C. All right, so there's Q hot and Q cold. So the efficiency then is just 1 minus Q cold divided by Q hot. N and R will cancel out, and we're just left with temperature cold times the natural log of Okay, just a little pause there while I realize my error. Okay, this is going to be the natural log of VD over VC, right? And this is temperature hot, natural log of VB over VA. All right, but what's the mistake that I made? Well, Q cold is not equal to Q from C to D, right? It's not equal to that. Because remember, Q cold has this other definition, that it's positive when heat flows out. So I need a minus there, I need a minus right there, so we'll put a plus right there. How's that? Or better yet, let's leave the minus here, but let's put an extra minus right there. All right? And I can take this minus 1 and bring it into my exponential, and that's just going to flip. So it's going to be VC over VD. It flips my ratio, right? I get a minus 1 there. Temperature hot, natural log of VB divided by VA. So there's my efficiency, except what is VC, VD, VB, and VA, right? That's kind of annoying that we still have those there. But it makes sense that we're not done because we have not used all of the information in the problem. In addition to the isothermal processes, we also have the adiabatic processes from B to C and from D to A. So let's consider what happens when we go from B to C. B to C is an adiabatic process. And as you recall, for an adiabatic process, all right, the temperature times V to the gamma minus 1 is constant. So when I go from B to C, that means that the temperature at B times volume at B to the gamma minus 1 is equal to the temperature at C times the volume at C to the gamma minus 1. All right? But the temperature at B and the temperature at C, what are they? That's when A to B is when my gas is hot, and C to D is when my gas is cold. So C and D are temperature cold. So temperature C is also temperature cold. Now I chose those letters carefully so we wouldn't get confused. C is also cold, but B, point B is when the gas is hot. So I can rewrite this as T hot VB to the gamma minus 1 is equal to T cold, the volume at C to the gamma minus 1. All right, likewise, when we go from D back to A, temperature at D, volume at D to the gamma minus 1 must be equal to the temperature at A, volume A to the gamma minus 1, because they are connected by an adiabatic process, and this is true for an adiabatic process. Well, D is cold, right? From C to D is when we're cold. So I can rewrite temperature D as temperature cold, V at point D to the gamma minus 1 is equal to, and point A is when it's hot, VA to the gamma minus 1. Now if this is equal to this and this is equal to this, then this divided by this should equal this divided by this. So let's just take this divided by this, and I get VB to the gamma minus 1 over VA to the gamma minus 1. And that must equal this divided by this. The T colds cancel out, and I just get VC to the gamma minus 1 over VD to the gamma minus 1. All right, and if we look here we've got VC over VD, VC over VD, and here we've got VB over VA, all right? Well, let's take the gamma minus 1th root of these, and we can get rid of the exponents, VA, C over VD, and then let's just take the natural log of both sides, and we get natural log of VB over VA equals the natural log of VC over VD. So that is equal to that, and they cancel out, and the efficiency then is just equal to 1 minus T cold over T hot. So this is what we call the Carnot efficiency. It is the greatest efficiency that an engine can have. If you fell asleep during the derivation, here is the result that you should know. All right, that the Carnot efficiency is the highest efficiency that any heat engine could have, even in theory, and it's equal to 1 minus the temperature of the cold reservoir over the temperature of the hot reservoir. So what would it take in order for us to get an engine which is perfectly efficient? Either the hot reservoir has to be infinitely hot, which is not possible, or the cold reservoir has to be infinitely cold. It has to be 0 Kelvin, absolute 0. Well, wait, isn't that possible? We'll find out later on that it is impossible to get to absolute 0, to get a finite macroscopic system down to absolute 0. So there's two ways to state now the second law. One way is to say you cannot make a heat engine with an efficiency better than the Carnot efficiency, but another way to say it is impossible to get a macroscopic system down to absolute 0. All right? And we will discuss that at a later date. All right, there's the Carnot efficiency. Okay, now let's talk about what the second law can tell us. The second law is really awesome because anytime someone comes along and tries to claim that a heat engine has more efficiency than this, or is even worse, maybe claim that it's perfectly efficient, you know that they're full of baloney. I knew somebody once who explained this business venture he had. He said, we've got these power plants, right? They burn coal, they make electricity, but then they exhaust this heat. That heat is wasted, right? And so why don't we take that heat and use it to run another generator? And then we can take whatever heat's exhausted by that to run another generator. Well, that may be helpful because maybe our heat engines aren't perfect. They aren't at the Carnot efficiency, so maybe there's something to be gained. But really, when you think about it, what you're doing is you're saying I have some T hot and some T cold. I have my heat flow in, and it produces some work, but instead of exhausting right down to the cold reservoir, let's take the heat flowing out and use that as heat to go into another engine and go into another engine and so forth, right? But the point is, if this composite engine right here, it can't have a better efficiency than a Carnot engine, and maybe I would be smarter just to make one really good engine, right? That the maximum theoretical efficiency for this engine is the same as the maximum theoretical for all of these engines put together, all right? You just can't do better. These guys as a composite, you can't magically put heat engines together and make something with an efficiency that beats the Carnot efficiency, all right? So there may be, because of technical reasons, there may be something to be gained, but you can't just game the system and get a perfectly efficient engine by tricking, all right? Because if I use this combination, all right, here, to drive a Carnot engine, right, I can't spontaneously have heat go from cold to hot, all right? So the second law is really handy. It's sometimes tough to calculate things with it, but the great thing about the second law is we went to the effort of deriving it, now we believe it, and now we don't even have to calculate things. We just look and somebody says, this is how my heat engine works, here's its efficiency, and I don't even need to know how it works. I don't have to look at the details. I just look and say, does it beat the Carnot efficiency? If it does, you're wrong. All right, and I've had that actually happen in a physics colloquium as well, where somebody came and made a claim about something they were doing that violated the second law. And it was great because I didn't have to know all the details about what they did. I did not have to do careful calculations based on their actual system. I could just sit back and think, boy, this isn't going to work. You're wrong. All right, now let's talk about an approximation to something more everyday than the Carnot cycle. We don't make Carnot engines. All right, we do not make automobile engines that follow the Carnot cycle. That's a theoretical toy to help us understand efficiency. It's not very practical. So let's talk about a more practical cycle. The more practical cycle is the Otto cycle, and this is what we do in a car engine. So if I draw my PV diagram, an Otto cycle looks something like this. I start with a piston, and it's filled with gas as well as gasoline vapors. All right, the spark plug goes off, and what happens? Suddenly, the pressure, sorry, I'm going to start the cycle over here. Let me back up. What we're going to do, for some reason, the book likes to start right here. Let's not do that. Let's start right here. Okay, I'm going to start right here, even though I'm going to call this point A, because it makes more sense to me. I've got gasoline and I've got air, and I send off a spark plug. It burns the gasoline. What happens? That gasoline gives off energy very quickly. All right, so very quickly the gas heats up, the temperature goes up, so that causes the pressure to go up. And the idea is that happens fast enough, all right, that the volume, the piston doesn't have time to move. So suddenly the piston is at a very high pressure, all right? Now, so I've got this piston, it's compressed at its smallest point, all right? And now this gas goes off, so here's my piston, right? And I put all this heat, and then that pushes upward, all right? So I generate this heat, and then it's gonna push upward, and it's going to expand adiabatically, all right? So it expands adiabatically. This is known as the power stroke. It's doing work, right, on your drivetrain, all right? But once it expands to its maximum height, all right, it's cooled down, what we're going to do is we're going to now let heat out. So here's Q hot coming in. We're going to let heat come out, all right? We're going to put it in contact with a cold reservoir and get our gas back to room temperature. Okay, now in a real car engine, you don't want to sit there and wait for the heat to just come out, you know, to the environment temperature. So what you do is you actually open up a valve, all right? and you have a flywheel that this whole thing is connected to that keeps the thing, so you get this thing started. Your car has a starter motor that starts getting the pistons moving, and once they're moving, you've got this inertia in this flywheel that keeps this moving up and down, all right? So with each power stroke, you put more energy into the system, but a little bit of that energy comes back to help push the piston back down. So what you do is you open up a valve that lets the hot gas come out, and the piston goes up and down with the valve open. So it comes up here, it's expanded, you open the valve, it gets pushed down, comes up, all right? And as it comes up, it's sucking fresh air in along with new gasoline vapors. So we've expanded, we've done the power stroke, we've opened the valve, we let it go down and up again, all right? And we get to this point, so we kind of go whoop, whoop, come back to here. Now our air is cold, we're back down at this pressure, and we've got new gasoline in there, all right? So then the flywheel compresses us again and gets us back to the same point we started with. So we have A, B, C, and D. So just to go over that again, that's kind of confusing. Here, the piston is compressed, it's got gasoline vapor in it, the spark plug ignites the gasoline, and the pressure goes up suddenly as we put heat in from the burning gasoline. Then the piston is allowed to expand, it does work, all right? So at this point, the piston expands up, all right, it goes up, and the pressure goes down and the volume goes up, and it does work. All right, now we need to get back to this point right here. So first what we do is we're going to open a valve, and we're going to let the piston go up and down. All right, so gas comes out, right? Immediately the pressure falls down, and then we go down. So when we open up that valve, right, the pressure goes down, we pull in some new air and gasoline. All right, then we close the valve and compress it back down to where we started from. All right, now without going through all of the calculations, it turns out you can calculate the efficiency, and what you get is this, where here is the volume of the gas when it's compressed, and here's the volume of the piston when it's tall. All right, so V1 is when the piston's all the way down, and V2 is when the piston's all the way up. So if I take the ratio of V1 to V2, that's known as the compression ratio. So it turns out the efficiency of a gasoline engine depends on this compression ratio. So sports cars tend to have very high compression ratios. Now, why wouldn't you make that compression ratio bigger and bigger? The bigger the compression ratio, the hotter the gas gets and the higher the pressure as you compress it. All right, so there's limits to what your engine can take. A bigger, heavier engine can have a higher compression ratio and have more efficiency, but then you've got to drag around a big, heavy engine as well. So it's sort of a compromise. All right, now quickly, we've been talking a long time, so let me quickly talk about refrigerators and heat pumps. A refrigerator is basically a heat engine run backwards. So you have some reservoir at temperature cold, you put in some work that pulls up some heat from the cold reservoir, and then the work plus the heat you pulled up get deposited into your hot reservoir. All right? So Q hot is going to be the work you put in plus the heat you pulled from the cold reservoir. Both of those energies get exhausted here. All right? So if you have a refrigerator and you're like, hey dude, I'm going to cool my house, the air conditioner's broken, I'm just going to open the door to my refrigerator. All right? So the pump on your refrigerator, it puts energy in order to pull heat out from the refrigerator, but then the heat that's pulled out is exhausted along with the work out the back of the refrigerator. So more energy goes into your room. Q hot is going to be bigger than Q cold. So you're actually heating the house by leaving your refrigerator open. All right? Anyway, now how does a refrigerator work? Well, you can draw a gas cycle, a PV diagram, but the basic idea is this. Imagine I've got some refrigerant, some vapor, all right? Some gaseous medium. It's at room temperature, all right? I am going to use a pump and compress it down into a smaller tube, all right? So what I've done is I've done an adiabatic compression, all right? So the adiabatic compression makes the fluid, makes the gas hotter, all right? Then this hot gas runs through some coils on the back of your refrigerator. This is hotter than room temperature, so heat leaves the back of your refrigerator and goes into the room. So if you touch the back of your refrigerator, there's coils there and they'll be warm. All right, so heat leaves and this will cool back down close to room temperature. After it's come down to room temperature, you let it expand again adiabatically, and as it expands, it cools down. So now you take this cold gas and you run it through some heat exchangers inside your refrigerator, and your refrigerator then is hotter than this cold gas and heat flows in. Alright? Then you come back and you do the cycle again, you compress it. So that's how a refrigerator works. Alright? Now, how efficient is your refrigerator? Well, we don't usually talk about efficiency, we talk about the coefficient of performance. But like efficiency, what we do is we take the thing that we want and divide by what we put in to get it. For a refrigerator, what we want is we want heat pulled out of the fridge. So we want Q cold, and what we put in is work to get it. So this is the coefficient of performance for cooling mode. Alright, so the coefficient of performance for refrigerator is Q cold divided by work. Now, if you use an ideal Carnot cycle, alright, you'll get the best refrigerator you can get. So for the Carnot efficiency, the Carnot coefficient of performance, well, remember, Q cold over work, work is going to be Q, so Q hot is equal to work plus Q cold, right? Oh, I've got it right here. So work is just going to be Q hot minus Q cold, right? And if we do like an ideal Carnot cycle, theoretical, with our refrigerator, remember the Q's had stuff in them that divided out, and because of the Carnot, because we were using the Carnot cycle, we ended up with just T's. So it turns out the ideal Carnot coefficient of performance for cooling is just T cold over T hot minus T cold. So no refrigerator can have a better coefficient of performance than that, right? Okay, it turns out if you take a refrigerator, but instead you stick the inside of the refrigerator outside your house and put the coils on the back of the refrigerator inside your house, you have something known as a heat pump. In a heat pump, the idea is it's cold outside, you want it to be warm inside, so you put work in, you draw some heat from outside, and you exhaust both of them into your house. Alright? That's really awesome, because like an electric heater, it takes the work and it puts it into your house, right? An electric heater takes electrical energy, converts it to heat in your house. All the work gets converted to heat. A furnace, right? I burn something, and all of that work gets converted into heat in your house, except some that goes out in the exhaust, right? But ideally, you should be able to turn all of that chemical energy into heat of your house. The cool thing about a heat pump is you get all of the work you put in, that comes into your house, plus you're pulling some heat in from the outside. So it's actually possible with a heat pump to heat your house and get more heat into your house than the work you put in. But there's a limit to how much you can get in. Alright, so for the coefficient performance for heating, we're going to take the thing that we want, which is Q hot, divided by what we put in to get it, which is work. So the coefficient of performance that we care about is different if we're trying to cool something or if we're trying to heat something. The Carnot efficiency for heating, then, is going to be Q, instead of the Q, we're going to put in T hot, and work, again, is going to be Q hot minus Q cold, so we'll put in T hot minus T cold. So if you look at a heat pump, if you wanted to heat your house with a heat pump, if T hot and T cold are very similar, a heat pump is extremely good. It has a very high coefficient of performance. So heat pumps, why don't people use heat pumps all the time when they can be more efficient than a regular, electric heater or gas heater? Well, the point is they're not perfect, right? So there's going to be, you have this connection between the inside and the outside that heat can leak through and whatnot. So you want to be able to get a big gain to make up for the mechanical and imperfections in your system. But the very best efficiency you can get is the Carnot efficiency, and that goes down as the difference between the outside cold temperature and the inside hot temperature gets bigger. So at a place like Utah where it gets really cold, a heat pump is not as useful as it is somewhere where it doesn't get that cold, but you want to save on energy anyway, alright? So they are used, they're less used because when they're most useful are in places where your heating bill's probably not so big anyway. Another problem is they have moving parts. An electric heater or gas furnace, you just burn something, you get heat. Here you've got to have a fluid. It's kind of like a refrigerator, and everybody knows that sometimes refrigerators go out. You've got to replace the pump and whatnot. All right, but it is a cool thing you can use, and in certain situations it can give you a lot of efficiency. And that's the end. Oh, no, wait, that's not the end. I just want to talk really quickly. We talked about heat engines and whatnot. Electric cars, they're so much more efficient. They're not limited by the Carnot cycle. They don't burn fossil fuels and make carbon dioxide. So why do we put up with gasoline? Here's a quote from Richard Mueller. Gasoline stinks, it pollutes the atmosphere with carbon dioxide, and it is blamed for global warming and for nitrous oxides that cause smog. It finances totalitarian dictatorships and terrorists and drives us to war. So why do we put up with gasoline? Gasoline is horrible. We would love to get away from gasoline, but the problem is, what's the alternative? Right, we talk about alternative energies. We talk about solar cells and wind, geothermal, nuclear. Nuclear is maybe viable. Some of the others are useful, but they're not going to provide, at least not in the near term, all of our energy needs. But as time goes by, it's really conceivable that we could come up with the energy that we need without having to burn fossil fuels. But there's another even bigger problem. It's not just generating the energy, it's storing it and transporting it, right? If you use wind energy, what do you do when the wind's not blowing? You need a way to store it. If you want to get into a car and drive, if that car is not physically connected to the power grid somehow, it needs to carry its own energy. It needs to have a battery, right? Well, it turns out for the same weight, gasoline has 100 times the usable energy of the best rechargeable batteries. So that's why they're so stuck to gasoline. It's not just a matter of coming up with new sources of energy, it's a matter of coming up with ways to store energy. This is a really cool field to get into if you'd like to. This is a place where a lot of effort is being placed, and some big breakthroughs are eventually going to happen that are going to change the world. Figuring out how to store energy compactly in a lightweight, safe way. Now you can store energy with hydrogen. That's one thing people have talked about. Hydrogen blows up in a way that gasoline doesn't. Alright, so there's a lot of things to work out here. Some people have actually proposed using solar energy and wind energy to drive chemical reactions to make something like gasoline that then we could burn in our cars. And then you feel like, okay, well then that's horrible because we still have gasoline. But it's not, right? Because when we're making gasoline, we're pulling carbon out of the air, and then when we burn it, we're just putting back something we already pulled out. So that's a very viable option. Those are things to think about while you think about thermodynamics. And now we really are done.